We're now going to turn our attention to the hybridization and orbital model for bonding. We're going to start off pretty simple, and then we'll go up in complexity to see how different carbon-carbon bonds like single, double, and triple bonds are formed using the hybridization model. So let's start with about the most simple example we can do, and that's hydrogen. Hydrogen has an electron configuration of 1s1. And the s orbital, that means there's one electron in the s orbital. And if you don't remember from general chemistry, the s orbital is just a sphere. So it looks like that. And this one tells us we have one electron in that orbital, and if you want, you can even draw it in there. So for a bond, what that really is, we can think of that as orbital overlap. So in the hydrogen-hydrogen bond, what we effectively have are two hydrogen 1s orbitals overlapping. So let's say here's one with its electron. Here's another with its electron. And those will come together and overlap. And now we formed the bond between the two hydrogen. This particular bond is called a sigma bond. And what a sigma bond is a bond that's formed between the head-on overlap of orbitals. Now we're going to look at how bonding occurs in methane through a hybridization picture. And the structure of methane is a carbon with 4 hydrogens attached. So it looks kind of like this. Because we have both carbon and hydrogen, then we need to look at the orbitals for each. So we already know that hydrogen just has its 1s orbital with one electron, and it's spherical in shape. Carbon, on the other hand, if we look at carbon's electron configuration in the outer shell, 2s2, 2p2. So we have an s orbital, and then we have p orbitals, and there's 3 p orbitals. We have px, py, and pz. There's 2 electrons in the s orbital, 1 in each of the p orbitals. As far as what these look like, carbon's 2s orbital is a sphere, just like hydrogen's. Now the p orbitals are lobe-shaped. So we have p in the x direction, p in the y direction, p in the z direction. So what's unusual about methane, at least looking at the orbitals here, we have unpaired electrons in the p orbitals and an empty p orbital where bonding can occur. But we only have 3 directionalities of the p orbitals, so you would expect the bonds around methane to be just in those 3 directions. But if we look at the actual structure of methane, we have a carbon with 2 hydrogens that are in the plane. One is pointed out toward you, one is going back away from you. And the bond angles between all of the HCH bonds are 109.5 degrees. They're all consistent. And methane is actually a tetrahedral molecule with 4 equivalent bonds. So then that leaves the question, how do we get 4 equivalent bonds out of these 3 orbitals and this filled orbital? So what happens is these orbitals will undergo hybridization to become more stable. And a crucial aspect to our whole hybridization picture is that while orbitals will mix, the number of orbitals that go into a hybridization is going to equal the number of orbitals that come out. So you don't add or lose any orbitals during a hybridization. They just change through hybridization. So simply put, the number of orbitals in must equal the number of orbitals out. So in the case of carbon, we're looking at just the hybridization of carbon right now, and then we'll add in how it bonds with the hydrogen later. But for the carbon, we have 4 orbitals. We have the s, we have px, py, and pz. So we start with 4 orbitals, and these undergo hybridization. And in this case, all 4 of these mix together. So if you take something that's 1 part S, 3 parts P, you get sp3. That's our hybrid orbital. But that is just 1 orbital. If we start with 4, we need to end up with 4. So we end up with 4 sp3 hybrid orbitals. And what the sp3 hybrid orbitals look like, they're kind of large on one side and have a small lobe on the other side. So you can almost think of an s orbital kind of mixing in with one side of the p orbital. So now that we have a carbon with 4 sp3 hybrid orbitals, we can think about how those most effectively arranges around the carbon to space out as far apart as possible. And 4 things, the furthest they can separate is in a tetrahedral arrangement. So we end up with our carbon, and I'll draw the 4 sp3 orbitals tetrahedrally around it. It's kind of hard to see when we draw this because I'm not going to use dashes and wedges, but I'm going to put them in the same basic orientation as the tetrahedron up here. And when we draw these, a lot of times we just draw the large lobe, and we omit the small lobe just to make it a little simpler. So there's 2, there's the 3rd one, and the 4th one. And each of these orbitals, because up here we started with 4 electrons, those 4 electrons are distributed, and we'll put an electron in each hybrid orbital. Now we can add in the hydrogen. So each hydrogen we know has an s orbital that is spherical in shape, and those will bond with each of the sp3 orbitals. So now I'll just draw the hydrogen s orbitals in green. So here's 1, and it's 1 electron. And there's the hydrogen. Here's the 2nd one. The 3rd one, and the 4th one. So this is the orbital picture for methane.